now we want to talk about interpretation of our solution. First thing we really want to do is we want to check out the units of this solution to make sure that the units come out in volts or joules per coulomb. So units should be volts equals joules per coulomb. Is that the case? Well, the units are going to be the units of K prime times I times V, because the units of A are meters, the units of Y are meters, so the A squared is going to have units of meter squared. The denominator is going to have units of meter squared, so the meter squared goes away, and the only thing left with units is K prime, the I, and the V. So units of K prime are Tesla meters per amp, as you can easily reason out from the fundamental definitions. I has units of amps, and V has units of meters per second, giving us units of Tesla meters squared per second. Just running all that out. The amps divide out meter times meters, meter squared, etc. Okay, well, now what's a Tesla? Well, a Tesla is a Newton per amp meter, as again can be reasoned out from the definition of magnetic field. Multiplying that by meter squared per second, the meter divides a meter squared, leaving us a meter to go with the Newton, which gives us a joule here. And the denominator becomes amps times seconds. An amp is a coulomb per second. Multiplied by second, we just get coulombs, and we do have units of joules per coulomb, which is cause for some optimism. Okay, now let's talk about the meaning of phi b here and what happens as we move this loop away from the x-axis. Well, if we move the loop away from the x-axis, y becomes larger and larger. Now when y gets much bigger than a, then the a doesn't matter a lot, so that the a plus y over y, as y approaches infinity, is just going to approach 1. Natural log of 1 is 0, so that the flux is going to approach 0. Now it's a decreasing flux. The bigger y gets, the smaller the flux gets. And it's going to be decreasing at a decreasing rate. It's going to be decreasing concave up, which means that the rate of change, if we're moving this away at a constant velocity, the distance will be proportional to the time, and a graph of flux versus time is going to have this characteristic where it approaches 0. It levels off. That means that the flux changes more and more slowly. Now, with this kind of a curve, we're going to have a negative change in flux, and we do get negative over here. We're going to kind of ignore that negative, but that's something that's important to realize. So that the derivative of the flux is going to have to approach 0 as y approaches infinity. Well, what happens here as y approaches infinity? We have a y squared in the denominator. The a becomes pretty much irrelevant. The denominator acts like y squared, and this does approach 0, so that the EMF, the voltage around the loop, does approach 0. Okay, now if y is small, if you're close to the current here, then the y is not big compared to a. The a is big compared to y. And that's going to make the denominator act like just a times y. Okay, the y here is important because it's multiplying this, but the y here becomes less important because it makes very little proportional change in the term a plus y, or the factor a plus y. So that what's going to happen is this is going to approach, if you're close to the current source, you're going to have the EMF falling off in proportion to 1 over y. If you're far, it's in proportion to 1 over y squared. Now, that's going to give us a behavior that I showed here and kind of obliterated, so let's do it again. We got inverse behavior, so this is like 1 over ay. And then we have the inverse square behavior, which is going to give us a graph that's steeper here but less steep here, approaching 0. This is like 1 over y squared. And what happens as we move from close to far is we basically go from this curve to this curve. And when we do that, we get something that kind of behaves like this. And if we want to get an accurate graph, well, we're not getting a really accurate graph by doing this graphically, but if you want to get a more accurate representation, of course, of the actual field, you're going to multiply by the factor 2a squared k prime iv, which is what you have here over the denominator, and that's going to cause you to have to relabel the vertical axis, but it's fairly straightforward.